In this lecture, we will see the equivalent model and parameters of PV cell. So if you see here, this is the equivalent circuit of solar cell, and there are different equivalent models like single diode based, double diode based and all. So this is based on single diode. So if you see, there is a current source which is given as IPH, so it indicates photocurrent, right? So that is a light current that is coming out of sun. Okay, so this photocurrent will not be completely coming towards the load, so there will be certain current flowing through the diode. So then the remaining current will be coming to the load which is connected externally across the solar panel, right? So that's why this IPH is divided into both diode current and the load current I, right? And these resistors RS and RP indicate series resistance and parallel resistance of solar cell, which gives the some loss part inside the solar cell, right? And we all know the PV cell concept anyway, that is photovoltaic effect. It is nothing but a PN junction diode, and when sunlight with a certain specific temperature strikes the cell, the electrons will be crossing the barrier. This barrier is nothing but depletion layer or depletion region. Then it will be a short circuit across the depletion region, and if you connect any load, the power will be coming out of the solar panel, right? So this figure shows the dependent current source IPH with additional series and parallel resistors connected to a diode, and the actual current from the current source is determined by the amount of sunlight that falls on the PV cell, that is photocurrent, right? So the output current is having an expression. This is for a PV cell. It is equal to IPH minus I0 into exponent to the power Q into VPV plus RS into IPV by KTCA minus 1. This is an empirical expression. So here VPV is the output voltage of a PV cell. IPH is the current that is photocurrent generated by the solar cell. I0 is the reverse saturation current of the diode, because this part is nothing but diode current, because the coming out of the current, that is equal to photocurrent minus diode current. So this complete part is of diode current, in which I0 is the reverse saturation current and Q is the electron charge, which is 1.602 into 10 power minus 19 coulombs. RS is the internal resistance in series, and K is the Boltzmann constant, which is having the value given here. Tc is the temperature of the cell, and A is the diode ideality factor, right? So now let us discuss the output characteristics of solar cell. So the characteristic curve of a solar cell is an important concept to understand and measure how much power is produced from a solar cell, because since it is coming from a light, we should know how much electrical power is going to be coming out based on the radiance, temperature and all, right? For that purpose there is a characteristic. So this characteristic curve shows the current and voltage characteristics of a solar cell or a module, giving a detailed description of its solar energy conversion ability and efficiency. Okay, in the end the product of voltage and current is nothing but the output power. Okay, so this IV curve is basically a graphical representation of the operation of the solar cell or module, summarizing the relationship between current and voltage at the existing conditions of irradiance and temperature, because they are the base inputs for a solar cell, right? Irradiance, you all know it, right? We have discussed it. So IV curves also provide the information required to configure a solar system so that it can operate as close to its optimal peak power point as possible. We will come to know what is the optimal peak power point. And the basic characteristics of a solar cell are the short circuit current, or these are the parameters of characteristics. It is not characteristics, basic parameters of the characteristics. They are short circuit current, open circuit voltage, the fill factor, and the solar energy conversion efficiency, right? So if you see, this is the characteristic, and we have current on the y-axis, voltage on x-axis. So as the voltage is gradually increasing across the solar panel, the current that is going to be coming out of it is also increasing, right? Sorry, it is not actually increasing. If you observe here, the IV curve is this one, this is PV curve. The power is increasing with respect to voltage, but whereas IV curve, if you observe, the current is maintained constant, okay, and after a certain point it is completely coming down with respect to voltage, okay. So for this IV curve, if you get a product of I into V and versus V, you will be getting this plot, which is nothing but P into V curve. So are you getting? The P is nothing but I into V. If you take product of I into V at a particular voltage, that versus the same voltage will be giving this plot. So this is coming because of this variation in current after a certain voltage. So after this particular voltage, what's happening? The current is going to be reduced as we increase the voltage across the solar panel. So here the short circuit current is ISC. It is nothing but the current through solar panel when voltage is 0, because at short circuit voltage is 0. Similarly, we have open circuit voltage. This is the voltage at which the current through panel is 0, right? You can see here the current is 0 at this point. So this is nothing but the voltage axis. So this voltage point is open circuit voltage, right? So you can find PV curve here as well as IV curve. This is the characteristics of, or our output characteristics of solar panel. Fine. So as I said, when solar cell is open circuited, not connected to any load, the current will be at its maximum. Current will be at its minimum, because there is no current in open circuit, and the voltage across the cell is at its maximum, known as solar cell's open circuit voltage. And when solar cell is short circuited, the voltage across the cell is at its minimum, that is 0 for short circuit, and the current will be maximum, and it is known as short circuit current of that particular cell. And there is one particular combination of current and voltage for which the power reaches its maximum value, and the values of current and voltages at that particular maximum value of power are known as maximum current as well as maximum voltage. That can be observed here. See, this is the P maximum point, right? Okay, the point at which the power is becoming maximum, and the corresponding voltage downwards, and the left side corresponding currents are nothing but maximum current and maximum voltages. Remember and understand, they are not equal to short circuit current and open circuit voltage. They are less than that. Okay, right. And the point at which the cell generates maximum electrical power, and this is shown at the top right area of the green rectangle, right? And it is the maximum power point of the solar cell, so which we have shown here, maximum power point. And on IV curve it is shown here. Okay, so the ideal operation of a photovoltaic cell is defined to be at the maximum power point. So if it operates at that particular point, we will be able to get maximum power out of solar cell. So it is always desirable to operate solar cell at that particular point. In order to operate the device at that particular point, there are several algorithms which are known as maximum power point tracking algorithms, because that point has to be tracked. Okay, since the solar cell output voltage and current both depend on temperature, the actual output power will vary with changes in ambient temperature. This we will see in the next